Welcome everyone to this week's IPLD sync meeting. It's August the 24th, 2020. And as every week, we talk about the stuff that we've done last week and plan to do next week. And then we discuss any agenda items we might have. And I already see that we have an agenda item. That's great. I start with myself. I don't have that much to report. I got a bit of time on Friday to work on Rust IPLD, but not really working on any new stuff, but just reviewing a PR. But that's a pretty big refactoring one because it's using the stuff that's not heap allocating, but stack allocating stuff for CIDs and multi-hash, and also a few other changes. One interesting thing for other implementers that might be cool is, David, a guy working on Rust IPLD, had an idea about codecs. So in Rust, it would be nice, or what we do is that you can serialize directly from native Rust types into a codec. So let's say from native Rust types directly to DEX-CBOR. And you can also directly go to DEX-JSON or whatever you like. But the problem is that sometimes you don't know where you actually want to go. So you first want to go to IPLD. So most implementations first go from native types to an IPLD type, and then from IPLD to wherever. And in Rust, you might want to take this shortcut. But sometimes you don't. And the problem is that in the past, we had kind of different APIs to do those things. So either going directly or going through the IPLD intermediate step. And the idea he had was we create a trait, which is kind of like an interface in other languages. And what you do is you implement this trait for the codec itself, but you could also implement the trait for an enum containing multiple codecs. So this way, you can go now directly from one native types to a specific codec, or you implement this enum for IPLD. So you basically have the same API going from native types to IPLD and back, or you have from native types directly to a codec. That's kind of smart, I think, and might work well, and might also be an idea for other languages that you kind of, combine an interface which can be used by multiple codecs or by a single codec. It's kind of neat. And next is what I try to do is that getting the changes from tiny multi-hash, which is kind of a fork of Rust multi-hash, get those changes upstreamed into the proper one. Yes, that's all I have. Next on my list is Peter.
Yeah, I still have no IPLD specific updates. At the end of this meeting, I'm going to space with a lot of other people on the Filecoin network. We're starting space race at midnight, so.
All right, next is Chris.
Hey guys, I did not die, so I'm back from extended vacation / personal leave. I could fill you guys in more on that if you want to know at some point, but I got assigned to build a JavaScript graph sync library. So that's what I started working on today. There's a link to the repo if you're interested. There is, I don't know how you guys do your dev process normally or how you've done it, but I did actually create a requirements documents in Google Doc that if you have time and interest, you could look at it and provide feedback if you think there's something missing, especially if you are familiar with GraphSync. I did go over it with Michael and scrubbed it a bit today. So that's there. And I did start implementing some things. I could use some help just to kind of get bootstrapped on the Go GraphSync side of things. I have a few questions. I know Michael said maybe Peter or Eric could fill in a few things. So if you guys have time, I'd get something on the calendar to do that. Since Hannah's like super busy and hard to kind of pin down right now. So anyway, that is my update. And I do have an agenda item about this multiple CIDs per block, which will probably be controversial and shut down, but at least I want to understand. So we'll tackle that later.
All right, thanks. Next is Eric.
Hello.
Hi, by the way.
Sorry I was slightly late. I've discovered that my computer doesn't do network time sync, and it's 7 minutes off today because quartz clocks are apparently technology is wonderful. So I worked on some documentation this week, and there is a new primer document that I wrote, which is trying to be an all-in-one sort of like try to fit into one contiguous page, just scrolling no links, piece of reference material for what is IPLD and what are all these things inside of it. This is currently residing in a HackMD sort of scratch pad, so anybody can edit it. So go nuts if you're so inclined. I'm not actually sure if I'm going to try to work this into our formal documentation or some offshoot of it, or like what the trajectory is for this, because I want to keep it terse. I don't necessarily want to evolve this particular document into a document for everyone. It's actually too long already, the way I wrote it in the first draft, I think. And so something that's slightly more opinionated might be part of its future, but I'm not sure. I'm just trying to like flesh out these different kinds of documentation that I think we might need. We've got lots of rich things, but I think we need more terse things too. So I made a shot at it anyway. So feedback welcome. I've got a PR out for adding a bunch of new tests and fixtures to the schemas and the cogen stuff in Go. Started using JSON for shorthand for tests, which on the one hand gives me the heebie-jeebies because that's kind of a large dependency tree of other things that you're assuming to work for your tests. But tests for all of our JSON stuff do already exist, leaning just directly on the basic node implementations. And so all of this stuff can be tested without, there's no cycles in this dependency graph. So if I had to bootstrap the whole thing all over again, it would still be a clear like progression. So I think it's going to be okay. And it saves a lot of line count. So these fixtures are also like probing everything at once. So you give it like a piece of JSON for the type level semantic structure, and you go to another piece of JSON for the representation, and it'll like make sure that these both produce the same data in memory and can go in every different direction. So this is doing more effective coverage with less lines of code, and I've already found a couple of bugs with it. So yay! And the traversal package in GoIPLD Prime finally has a get function, which just plain gets you the thing that you asked for by path, as opposed to making you go through a whole callback rigmarole. So people have been asking for that for a while, and I finally did it. Long overdue. And that's about it.
Thanks. And next on the list is Rod.
Hello. Mine was a light week. I took a little bit of time off. I've had some couple of health issues, but I tidied up the Hampton AMT work in Filecoin and handed that over. So that's out of my hands, and they've apparently assigned someone that will be taking charge of those libraries, which is great. And as you can see by my links in there, I put links in the notes to the work that I did in pull request form. The HAMP finally got moved over to the Filecoin org, which is where it should live, to clear up any misconception that this thing is a generic thing. So that was good to hand that off because it was a lot of work, and they've said that they won't be accepting the breaking block format changes. That was objected to up the chain because it's just too close to launch, which is fair enough. It's that I think one of the biggest concerns is now they're trying to build a lot more integration type testing for the whole system where you get consistency IDs for different operations, and they're already working on live data. So breaking block format changes sort of stymies all that. So that anyway, that's fine. I did that stuff because it would be good to do, but it's all, and I knew it was in their hands, and that's fine. But those changes may get pulled in during the next major network upgrade, whenever that happens, if ever that happens. Who knows how that process is going to roll out? That'll be interesting to watch, but it's there for them, and I think there would be good changes. It does leave us, though, with the HAMT. One of the aims with this work, other than just trying to improve it, was to pull it a little bit closer to what we would produce as a generic HAMT, as an IPLD offering, so that our work could more easily overlap with theirs. And so it would be fairly simple for us to have some code that could work for them as well as for anyone else. And it wouldn't be a big leap between ours and theirs. So all it means now is that theirs is producing blocks that don't really look quite like what we would produce. But it's not, the distance is not huge. It's just a little bit annoying. So that's all. I spent some time in JavaScript ES modules stuff, converting some code and trying to understand Michael's new stack. And yeah, there's a lot of pain to be had there. But they were my major highlights for the week.
So next one who doesn't have put anything on the agenda on the list, but Michael, do you have any updates?
Yeah. Sorry, I'm like bouncing back and forth between a million things. So earlier in the week, I really finalized the all of the ESM migration stuff. So we have like actually good tooling now there that like really does the right thing and is pleasant to use. And I migrated basically every module that we have on ESM to that. So multi-formats all the way up through block, and then all the things that block that depend on block as well. And all the way up to DagDB basically. So DagDB, I have a branch right now that I'm working on where I'm doing that. And then on Thursday, I had the idea for this block format, and then that captured all of my attention for the rest of the weekend. And I won't get into that a ton now because I actually prepared some slides to go over and just talk about it in the call in a little bit. So I'll let all the other people finish their updates and then we can talk about the block format.
All right, so I guess, yeah, so the most important thing I forgot at the beginning is that, does anyone new want to introduce himself?
Yeah, I probably should. I got started today. My name is Daniel. I joined the IPLD team. Just to give a very brief introduction as to what I do, I mostly do Go and open source. So I know most of you are from other backgrounds. So I'm actually interested in learning a little bit of Rust maybe someday. But anyway, all that I've done today so far is really just getting set up with the accounts and reading stuff. And tomorrow I hope to actually get into some code, but that's pretty much it. Nothing else for me.
Cool, thanks. All right. So yeah, so we have an agenda item. So I guess, so what should we do first? I guess first the agenda item, and then Michael can do his presentation, or any preference?
Yeah, let's do that.
Yeah, okay, so Chris.
Yeah, so I know we've kind of talked a bit about compression and encryption in the past, and kind of one of the key objections to it was it kind of breaks the content addressability. And so kind of the question comes up, well, why not have, I guess, multiple CIDs because associated with a block, one which is like a semantic CID. So that would be one where it's like uncompressed, unencrypted. But then you could have other CIDs which refer to that same block. It's like a lookup mechanism that would be the actual encrypted or compressed version of it. And so if you think about it from a from an existing tooling point of view, a lot of IPFS works with basically a single CID per block. And so if you're doing bit swap or graph sync or something like that, that could use the I guess as stored, but we could, I'm not sure exactly the best way of doing it, but just the idea is that to allow like different identifiers, kind of breaks content addressability, but it does allow essentially the stored format to vary depending, independent of the content, but still keep the content addressability in a sense. I don't know if that makes any sense, but that's the high level question idea.
Okay, does anyone have any comments? Because like I honestly have to think about this. Like that's like yeah, yeah. Does anyone have any thoughts now?
We don't have a way with CIDs right now to differentiate on that level. That would be my biggest concern is, okay, I've got a CID, what is it for? And CIDs are supposed to have that information. Maybe if CIDs had a mechanism, or if we use different codecs to say, this thing is a compressed container of this other thing, maybe that would be reasonable. Because it's not unreasonable if you just came up with a codec for just compressed or zip something, then maybe that's all it is. But I'm not sure what that buys you.
Yeah, like for example, GraphSync is not really centered around like per CID round trips. It does have batching and and things like that. Or okay, in theory, in spec it does. Like the way Go GraphSync works right now is a little bit more primitive than that, but that's ongoing work. So I guess to echo Brad's question, what does it buy you to basically have a jumbo block of in a sense?
To have a what? Sorry.
A jumbo block in a sense, like with multiple CIDs.
Yeah, an intermediate. Yeah.
Well, so I guess what I'm thinking about is that if you have one block linked to another, you would. So so we all understand the use case or the need for encryption compression, right? And I think the feedback I got was that, well, you break the content addressability. So if you link from one block to another, think about this. If you did, let's say you like what people do today is that they'll encrypt content and then stick it in IPFS. Well, then you kind of lose all of your linkability because now your links are encrypted in that block, and to actually traverse them, you have to decrypt the block, and so it's not going to work with things like GraphSync or anything else really. And so the idea is like, well, what if we had like a semantic, like the way it is today, there is no encryption or compression and everything. And so if you linked from one block to another, you would still use essentially the unencrypted, uncompressed CID to link between blocks. But then, and so you could traverse the graph that way, but then underneath it's actually could be stored compressed or encrypted and therefore moved from one IPFS node or one node to another, preserving that compression or encryption. Not have to actually undo it or decompress, de-encrypt, send over the network, re-encrypt, recompress. I know it's kind of abstract and I need to think about it more, but I just kind of wanted to throw it out there because, like I said, when we talk about this in the past, I keep bumping on the fact that we break the content addressability. And so to kind of preserve the content addressability, it's almost like you need different identifiers, different ways of identifying the same block. One which is, like I said, the semantic or uncompressed, unencrypted version, and then the one where it's actually on disk.
The way we've talked about, one of the ways we've talked about encryption before is to essentially have a block that presents itself as an opaque container. And to navigate it, you need extra information, but it presents itself as a normal block. And when you read it, you have to apply some logic, which is where advanced data layouts come in. So if you read a block and you know that it needs some kind of logic, then it goes through the ADL pipeline, which is starting to exist in Go. And then in there you apply the logic, which inserts a key and does some encryption, and then presents the real block format in there. And so in that sense, you would have sort of what you're getting at, but you don't need that second CID. It's the CID is the CID of the encrypted data. It's just that to read into it, you need extra logic. One of the problems we have with encrypted blocks in particular is because all the links are all hidden inside the encrypted data. You break the graph unless you can encrypt at decrypt at every stage. And it's not and if you're just an intermediate storage service that is just storing them, and and you want to do some sort of graph sync exchange, then unless you're given the key, you can't do that full thing. And so we did throw around some ideas of where you could extract links that are not sensitive outside of the encrypted container. And so you present the block with some, a link section and then the encrypted payload. And so you could still traverse enough of the graph. And for some use cases, that would work just fine, because the link section would just be a graph of all these encrypted blocks, and they'd only expose enough information to be useful. But there are other use cases where links are going to be sensitive. Like you might be linking to some particular external source that actually gives away what you're encrypting, or gives a suggestion about it. So this leakage of information. So it's a bit of a hard problem to solve. But and as this, we did talk about the same thing working with compression, but it gets so sloppy with compression. It really does get messy when you're pulling compression into the block layer. There's so much that it messes up, particularly for compression algorithms that are not deterministic, which is something that we've been talking a lot about recently. Is there really a solid compression algorithm that is actually provides compelling results that is deterministic? There's plenty of them that provide okay results, small amount of compression, and they're fast and they're deterministic. But would you bother using them if you actually wanted compression? You'd reach for something that can do decent sized compression, and a lot of those are not deterministic.
You're stealing Michael's thunder.
No.
Yeah,
well,
that's right. And yeah,
I was just gonna say like just to show kind of how data specific this is, right? Like I've been experimenting with this new block format, and one of the advantages is that the links and the values and the structure are in different sections. So you can actually compress them separately and kind of play with that. And you get the links, which are just hashes and aren't going to compress well, and you know that out of the way. But even if you look at like the Filecoin chain data, none of the value data in the Filecoin chain compresses very well. It's like a maximum, I think, of like 3%. And so that's just like not actually worth taking the parsing and decoding time. And that's probably because most of those byte values are like public keys or something, right? Like it's all like actually encrypted byte data. So you do have like these incredibly domain specific like compression needs. And then, yeah. I mean, I'll talk about my block format a little bit, but you can start to actually program these into the data structures if you have a block format that has a natural compression scheme.
Yeah, and I know I won't use much more. I just want to throw that idea out there, and I'm sorry, I'm kind of like brainstorming it on the fly here because I haven't fully thought it out. But one, I'll just close up with this. It just kind of occurred to me that maybe the right way to solve this is at the transport layer. And so from a client point of view, you're always working with the CID, but there's some optimization at the transport layer if I want to basically move an encrypted block from point A to B or a compressed block from point A to B. That's purely transport negotiation, but in the end, once I start working with it directly, it's the full content addressability. I think, and right, I mean, one thing I don't necessarily agree with, I think that you can have deterministic compression. It's an area I've done a lot of work with compression in my career, so I know a lot about it. So I don't know why I think I understand why we think that's not deterministic, but it's more about just controlling the implementation as opposed to saying like algorithms, like compression just isn't deterministic because it is. It's just code. You've got control. You have to control it such that it's not like there's no random number that's part of compression. There are parameters and there are certainly different strategies you can implement for a given compression format, but that can all be controlled just by controlling implementation.
Well, my biggest concern there comes from this stuff with trying to make even DAG seaboard fully deterministic. Is that compression algorithms generally provide you with many ways to compress the same data that will decompress with the same algorithm. So the decompression side is this asymmetrical thing that goes on where the decompression will look at it and say, yeah, I can decrypt that. I can decompress that. And whereas on the compression side, you can choose any number of ways to compress the data into a format that the decompression will be happy with. And so we end up with this problem of the same data, many CIDs. And what we want to do is reduce that possibility. So if we were to spec a compression into our formats, like Michael is trying to do, it would have to be a way where there's only one way to decompress, and sorry, one way to compress and one way to decompress. And if you were to, and on the decompression side, you ideally should be able to verify that it was compressed in that one way, whether that's it had the same dictionary or the same parameters for the algorithm. You'd want to be able to say, yes, this has gone through that one way, and it's not some same data that I've already seen before, just decompressed with slightly different parameters. We want to minimize that as much as possible, so that, you know, like, actually we want to eliminate it if possible. But we're finding that even hard to do with just DAG CBOR.
This is like a nice transition point, but I'll get into this a little bit. One of the cool things that I've been noticing is, okay, so first of all, as I've been writing this block format, it's in order to be deterministic, you have to only ever have one way of doing something, right? Like, you cannot have variability, you can't have optionality. It has to always be the same way. But that is like no variability in the structure. And if the structure itself supports a certain form of compression, what you end up doing is just adjusting your data structure to fit that. And then you don't end up with algorithms changing the deterministic representation, right? Because the representation that you spit out is going to be chunked differently and is therefore actually different data. Like, if you have a different array of bytes, right? That is literally different data. It is deterministically different. And what a lot of these algorithms are doing is figuring out what the layout should be of the data in order to compress it into a table, right? Whereas if you separate that from the actual format and you say, like, oh no, we only have one way to encode an array of bytes, and it is deterministic, but we will compress and we will deduplicate every one of those bytes. Now all of a sudden, like, you can write multiple decompression algorithms that all spit out different data structures, but each one of those data structures can be deterministically serialized and deserialized. Does that make sense? Here, this is a good point to actually start the talk, because then here, I'll show you this new block format, because it'll all make sense towards the end of it.
Can I just make one quick comment? Just real quick. So one of the general things I think is that doing some compression, any compression, is better than doing zero compression. I think that's one kind of rule of thumb I've lived by and heard many people say. And so I think it's not about having the most effective compression algorithm, but it's just doing some, and actually higher compression algorithms that are very fast, like deflate extremely fast. You can almost do a mem copy speed. It would be good, rather than doing like gzip level 9, just doing gzip level 1 is like better than like nothing. So anyway, I'll hand it over to.
And I think those simple formats tend to be the most deterministic as well, because they're actually simple algorithms. Yeah. But
again, like, I tested this against the Filecoin chain data, and even there, like, it's only 3%, because that data is just not really actually compressible, because it's all like cryptographically generated. So it just does not, it's actually not worth, it literally is not better than doing nothing, because it takes twice as long to serialize and deserialize. And that's not worth a 3% gain on the block format.
Yeah, just one thing, specific on the comment that some compression is better than no compression. If you do deflate or gzip 1, then you cannot do a gzip 9 anymore over that. So there is a good point. Definitely the trade-off of, if you compress once, you cannot double compress or anything like that.
Yeah, you don't double compress. But I mean, I'd argue actually, Michael, that your Filecoin blockchain data is already compressed. So I'm talking about just basically because you're using varents everywhere, so it's like it's going to compress fairly well.
No. I'm talking about just the raw data out of Filecoin, like decoded into CBOR and then round tripped into my thing. So like, I shave more bytes than 3 off of it because of other things I do in the block format. I'm saying just the difference when I took the value data and compressed that only like lessened it by 3%.
All right.
And this is going to be use case dependent. Like, if you take the average IPFS data, which is a website, then you're going to actually get some benefit from there.
Right. Okay. All right. I haven't even named this yet. Okay. All right. ZDAG. All right. So I had this idea on Thursday, and then I didn't stop working on it since. But effectively, so it's a block structure that looks like this. You have a links header and a values header, and then the actual structure of the data. So you front load the links, and then you basically have all the value information, and then just a structure printout. So the link encoding looks like this. So first you sort it based on like a CID specific sorting algorithm, so that we can then, so first of all, there's no delimiter between these because we know what the decoding rules are for CIDs. So the only delimiter that we need is a null byte at the very end of the links header. And then because we sort them all this way, we can then shave all of the prefix bytes off of every different CID type. Since you only put these in here once, this is effectively a compression table. So now whenever you refer to these CIDs in the rest of the structure, it only takes 1 or 2 bytes depending on the container format, because it may or may not need typing information. We do the same thing with the values. We take all the values, we sort them first by length and then by byte comparison. And then when we store them in that values header, we put the length in front, but we put the increase in the length. So if you look at this, this is 4 because it's increased from 0, and then it's 0 because this one is only 4 again, and then 6 length gets 2. This keeps the actual length integers in the values header low and actually compresses even the representation in the table down a little bit further. And as you parse this, you need to validate its determinism. The length is easy, but you also need to do the byte comparison because you will rely on the deterministic sorting of the values header later on in some stuff that we'll get into. So if you look at the structure, so here's just like a simple list. So numbers under 100 don't conflict with my token space. So they're just inlined basically. And then numbers over 127 are also are just var ints basically. So we inline most numbers without any additional typing information. Only some stuff in the token space is taken up. So that's what a list looks like. We omit the trailing delimiter when it's a root structure. Also, when there's no links or when there's no links or values, we can also drop the null bytes with some extra rules as well. So I've been shaving a lot of bytes off of this format, as you can see. Here's like a list inside of a list, right? So 109, 1, 109, and then 2, 3, and then end delimiter, and then we can omit the trailing delimiter because we know that the root structure is a list. So that's pretty nice. Like we get like a nested list here with 3 values for 6 bytes. You can see null, true, false are also constants that show up in here. This is what that serialization looks like for that kind of a list. Okay, let's look at some fun stuff. So this has no links in it, so we get a 0 byte to delimit the links. This header value is wrong. Sorry, that should be 12, not 10. So then we see 5 for the offset. Then we get hello in binary, then 0 because the next one is also 5. Then world. Then we say that it's a map. Then I'm playing around right now and poking at the map offset rules. So some of them in this example may be a little bit different. So this is so the map is basically first the offset for the key in the map, right? So that's from 1, and it's I'll talk a little bit later, but like the first key in a map is always offset by 1, and you have a separate token for empty maps, and this is so that every subsequent key reference is an increase in the offset from the first one. And so it literally conflicts with the trailing null delimiter to end the map. So it's impossible to actually write out indeterministic maps. You rely on the deterministic order of the table, and then you only see the increases here. And you actually have a rule that means that you can't even parse indeterministic maps, which is great. And then you see that you also have the value index, obviously. This example is wrong because this is an untyped map. So that there should have been a trailing string byte there. So it should have been something like 103 or something like that. And then the 1. I literally wrote these like late at night. Here, so this is like, what a more complex object with more values in. But you can see that like the compression starts to set in here. So, I'm referring to the same strings again, and so they're just going to be deduplicated down here, and they're not going to take up a ton of extra space. But this is something that I'm just working on now. So this is typed lists and maps. So when you have a typed list or a map, you can drop that the typing prefix from it, and then you get a much more compact space. So here we have a string type list. So this is just going to be like all the values. I don't have the new, oh no, this is a list. So it's always, yeah, it's always the index +1 so that you can use a trailing 0 to limit it with these typed lists. But that means that now like the compression space for a typed list, when you don't vary the typing in lists and maps, is actually really, really small. Like we can get really effective representations. And an idea that I had after talking to Rod actually is that for the rule set for parsing out these references, we can actually say,
he just killed his.
We'll never know what we can actually say.
Cliffhanger. Wow. Cliffhanger.
Yes.
There he is.
The fire nade took him.
Okay. Sorry. I messed that up. Sorry. Yeah. So I hit the wrong button to end the presentation and actually exit that thing. So anyway, I'm talking way too fast because I'm very excited about this. But yeah. Anyway, what you end up with are like these just very efficient representations. So my testing on the Filecoin chain is that this is going to reduce it by, like, when I'm all said and done, about 10%, I think. Like, I think we're going to shave about 10% off a DEG CBOR. And that's not really taking advantage of any of this deduplication, right? Like none of that data has any duplicate CIDs or binary values in it. Like the only savings that you're really getting on that 10% is just the more efficient representation of the links and of some of the other bytes that I'm able to shave off of the format, leveraging the determinism. But you can, now that you know that this feature exists, right? If you know that you can always deduplicate, you can do stuff like write domain-specific compression algorithms. So you can start to like chunk up your data and alter your data structure so that you always leverage this deduplication, because you know that, like, so if you keep the value table or the link table below 100, or sorry, not below 100, below 255, all of the addresses are going to be 1 byte for the whole table. Once you go over 255, then it's a var int, so it can be a little bit bigger. But we basically have like this maximal space for that table. And when you work your way through it, like, you can really start to design some crazy data structures that are super compact because of just how they leverage this compression inside of the block format. And the nice thing about it is that, like, all of these domain-specific algorithms for how to lay out the algorithm are specific to the application. The block format will just decode all the time, like without knowing any of those algorithms. Another really cool thing is that because you're putting all of these in a constants table, the reduction in the size of the block from the deduplication is also translated into the memory overhead when you parse the structure. Because when you parse them, they're also going to come out as constants and then just references back. So they're always going to be pointers. Unlike when you go through like JSON or CBOR, every time you see a string, you always turn it into a new string, and then you have 2 of those in memory, unless you like think to go and check those and deduplicate them, right? So yeah, like it is kind of crazy, because what it really is it's a block format as a compression table, right? It is like a block format that you can program with IPLD to compress the data representation. And so you can just like do very different things with it than we thought about doing them in the past, right? And like when I take like the optimization that the Rod gave me the idea for, and some other things, like you can take a subset of this and just say, okay, we have a byte typed list, and then just references to the table. So now it's just like a very good generic container format for any domain specific compression algorithm that would be fully transactional. So you don't need, if you're not going to do a streaming algorithm for compression, you can almost always write a more efficient compression algorithm that uses this block structure. And then you just get back like an array of bytes that you put together. And so you could literally like write a standard where that's just now a general compression format, and you just decode it with bytes, right? And then for us, those things are always going to decode as valid FBL segments. So you can use them as an FBL, you can stick them inside of other FBLs, and they just work.
So it'd be great to see some more examples, and I think just to work it through. One thing that I've been working on is something called CBOR LD, So CBOR linked
Mhm.
data, where it's using pivoting off of JSON LD, where you can create int as keys based on an external library. There's a great discussion about this at the IETF working group, CBOR working group, just like 2-3 weeks ago. The challenge is that you need to have a cryptographic hash in order for that external library. And then right now, the ordering of the key, the attributes of the ints is basically determined by the serialization algorithm. And so if you throw a different dictionary in there, you actually can offset it. And since we're dealing with cryptographic material, you can actually, like in most cryptographic libraries, will take null and validate null as true or valid.
Mhm.
So there's a big vulnerability right now we're trying to sort of work through. And I'm suggesting using CIDs as the link for the external library.
Mhm. Yeah, I mean that's a really good idea. I don't like one of the things that messes me up a little bit about external tables is that they really mess with the determinism of the data structure that comes out, right? Because you can take the same data structure and then apply a different table, and then you'll effectively end up with the same semantic data out, but it'll be a different hash for the block format, right? And so the nice thing about this is that the only information that is ever compressed is in the block, and so it is fully deterministic to the block data. So there's no way to take different block data and get a different hash for the block out of it ever. Right.
Mm-hmm.
But that is a limitation on the compression, because you may not want all of your compression table or the low end of your compression table to be really small strings. There are like efficiency reasons why you may not want to do that, right? And you don't really have the ability to tweak that because it's deterministically ordered. So it's not like always the best compression table, but it is like the best like deterministic compression table.
There's a couple of interesting properties that I've been trying to think through that need more thought about this. One is the ability to validate a schema pretty efficiently if you just jump to the structure section. I think there's enough information in there to validate against any of our IPLD schemas. So if you were some intermediate party that didn't care about the contents of a block but needed to perform some kind of validation, perhaps you were a loader that needs to feed data into some ADL or something, and all you care about is this thing valid, then you should be able to skip to the structure section and just parse that, and there's no extraneous bytes that you need to skip over. It's all structure, and then that should be able to match against a schema or not, and you should be able to do fairly fast schema validation if you built that in at the lowest level. That's the catch, is that kind of validation would need to be built in at that lowest level where you could get into there.
Well, there's a real opportunity to do that though, right? Because one of the things that you want to do is that you want to be able to validate that a block is valid without parsing everything out of it, right?
Yeah.
And so like with this, you can actually run over the structure and do a validation just to make sure that it is like a valid ZDAG block, right? You like know that it's now a valid ZDAG block. It didn't do anything bad. It actually parsed correctly. And then if you have typing information that you care about inside of that structure, you can validate it at that time without ever taking any of the byte values and converting them to strings. Unless you specifically need to do a traversal through a string map key, then you would have to parse that. But most validation you can actually do without that. And there's some other crazy stuff that you can do too. Like if you want to check if a path is in there, and the map doesn't have any keys in it that match the length of the first one, you don't even have to parse the string out, right? Like you already know that it's not in that block. So there's a lot of like stuff that you get out of. And also, if you're doing a block traversal and you're just traversing to get a value out, you can do that without like most parsing, right? Like you can just parse through your path, and then you would only end up converting any of the strings out of the value table if they're the map keys that you traverse into, or if they're the final values.
The other interesting property that is interesting for our schemas is that the format makes, I think, all of our union types fairly cheap compared to what we have now with particularly JSON, but also CBOR. So you do get a saving for using a kinded union, but the rest of them are not that much more expensive than a kinded union to do in this format, because you brush away a lot of the extraneous data to, like with a keyed union, the key sort of is brushed somewhere else, and it doesn't even matter how big the key is. That's elsewhere.
I mean,
so
you still have to store the key, though. I mean, you do have to store the key.
Yes,
once.
but with kinded with unions, you tend to have repeating keys, and so like in the HAMT, you've got up to 32 elements with exactly the same key in a keyed union, and you don't have to store that once. Whereas with DAG CBOR and DAG JSON, you have to repeat it. But if you could just extract that out, then it's you save. And because that's the nature of unions, is they tend to be repeatable structures that you're using again and again in your data.
So one of the things that I definitely hit upon here is that because we don't type the map keys, we get to save that byte. And so for us, a map key as a string is the same as if it were a byte or an integer, right? It's not taking up any extra space because we don't actually relay any typing information. So that's actually quite nice. We're not hitting any of that stuff. But one thing that I will mention, though, is that this does give you an incentive to use maps or lists that are always the same type. So yes, it like when you're doing the map or tuple representations for structs and you have mixed types, we definitely shave down the size of that and make them pretty comparable. But if you're using a tuple representation struct and all of the things in it are the same type, then it's going to get way smaller actually, because we get to shave all of those type prefixes.
It'd be also helpful just to see some of these examples, because I think the example you showed was basically you're saying beginning of list, end of list. And so, but I think in the proper CBOR, looking at the raw block storage, you basically have to state how long, it's actually have to convert it to an array, and it's prepend how large that array is.
Yeah, we don't. Yeah, I don't do that because for a couple reasons, but one is just that it's smaller, because the length is going to often be larger than 0. So if 0 or a 1 byte field is going to be my delimiter, then putting a length in would be bigger. So there's just no point.
Yeah, but I think actually your IPLD spec states that there's no infinite size or undetermined list sizes. You have to basically state this is an int array of size 10.
It's right, but we don't enforce it.
No, hold on. The way that the data model works is that the data model only comes into play after the codec is being done parsed. So the parser can always tell you how big the length of the array is because it'll be done parsing it by the end. It doesn't need to be in the block format, right? Okay. Like we know that it's not an infinite length because the block has an end. So we definitely know that. And by the time that you get it back from a parser, it will have a fixed length for sure.
Yeah, this goes back to that thing before with compression that I was talking about, Johnny. Our current CBOR decoders, I don't know about Go. Maybe Eric's is more restrictive, but they will accept indefinite size lengths, and then just give you the thing at the end. Whereas when we encode, our encoders will do the size up front. So the encoders always do the same thing, but the decoders are sloppy, and so they will present you with data that looks exactly the same, but it has a different CID because it was encoded slightly differently. So if somebody produces an encoder, say in Rust, you're working with Serde, and maybe Serde does indefinite size length elements, they will be decoded properly. But if we do a round trip, we'll get a different CID. And that's the problem we keep on battling with CBOR. There's so many ways to do just simple things that it's crazy. And so one nice thing about defining a new format is that we get to say, no, there's only one way of doing that thing. You can't do it. There's no variability here. You can't do ints of different sizes. No, it's all one way. So that's an opportunity here.
And one more, and just one more point on indefinite size lists. If you combine them with compression, you actually don't know how big your block is.
Yeah, but like, I mean, the nice thing about only having one way to do things is that you can like just brutally shave bytes off of the format, because you don't need, because the lack of variability means less tokens and less differentiation. And also like the crazy thing that I'm getting into is that it also allows for less token conflicts with valid data. So like one example is that, like, in my opinion, being able to encode a 0.0 float is a bug in the determinism, because that is effectively the same value as an integer. And in a lot of dynamic languages, it won't round trip properly because it's the same thing. Like, you're talking about the same thing, you've just typed it in the block format rather than typing it in like the data model layer above the block format and converting it if you need a float or an int or whatever. So similar to variants, right? Like a variant, it's encoded in whatever the smallest space is. And then if you need it to be a 64-bit, you convert it to a 64-bit integer, right? Like that's what we do in the encoding layer. The same thing is here too, where like you're not allowed to do floats that are 0.0. And in fact, they will not parse or validate because we need to use that 0 byte for other things. Like, yeah. And that's why. Go ahead.
Yeah, I just want to mention what I also mentioned to Michael earlier today, because there's a format already existing which is almost the same thing. It's called Fleas. I post a link, and it's on my to-do list to implement this in Rust for like the past, I don't know, 6 years or something. But now that Michael came up with this, I think I have to do it, because I'm pretty sure it has almost the same properties. So of course it can't store CIDs because it's not built. So it's basically a format which is made for general JSON data, but more efficient. And also, but like a slightly different goal was that you can easily traverse the data without the need to deserialize everything. So you can easily hop through the data basically into deeply nested things quickly without deserializing all the stuff. But yeah, just bring it up.
So the reason why I don't think that that's that necessary of a feature for this is just because it is so cheap to parse through the structure, because all you ever hit are ints and variants that you're checking for all of the token space and anything that can come out of it. And then you're actually able to skip over anything that you don't care about.
Yeah.
Right. So it's actually like really simple to get. Like it's really not very costly to get from 0 to 100 in the index. So you don't really need like the skip list functionality. But yeah, I can see how that would be really useful if you were inlining anything ever, right? Like I only like that's only that efficient because we never have a large value there that doesn't get parsed like on its own.
But anyway, I'm looking forward to do a comparison, because now I have a reason to actually implement this thing in Rust.
Yeah. Also, like another thing that I think is really important is like we have a lot of numbers all over the fucking place in our data structures. And so I really wanted the number format to be as compact as possible. So everywhere that you parse a value, var ints basically get inlined, and then the token space just, if you do a var int that conflicts with the token space, then you get a penalty byte. But most integers are just completely inlined without any additional typing information needing to be in front of them.
Okay, we are almost out of time. Anything else from anyone?
I guess a real quick question for Michael before I have to run. What is next step? Like, how ready is this to to implement and all the things to put in the Filecoin blockchain?
No, it needs like tests and like needs to feel somewhat done before you start like saying that people should use it for real things. We don't want to take block formats willy-nilly, and also like I don't want to stabilize on this until we're done actually working on the format. So I have like at least a few weeks of just poking at it and tweaking things and seeing how many bytes I can shave off of different pieces and experimenting with different data structures and stuff like that. Like I have a few things that I want to run into it to see how efficient a lot of the table stuff is before I move forward. So there's a bunch of just like more. I mainly wanted to get on everybody's radar because it changes the way that we think about how to create some of our data structures if we potentially have this compression in the future. And there's just like, it's a good thing to have on people's radar. But I don't think that we're going to be ready to actually move stuff to it for a while. I think maybe in like a month or so, we might want to look at doing another implementation. By then, like, I should have actually like stabilized the format. I mean, like, you know, I've only been working on it 3 days, so I've broken the format every day and like changed things and moved them around. And you know, there's stuff like the token space is not in the exact right position that I want it to be in. So at some point, I've got to like decide how many tokens I'm going to have, and then I'm going to like fix it to that space, right? And I'm going to decide where I want the tokens so that I can do better math and things like that.
Okay, then I close the meeting. So thanks everyone for attending, and see you all next week. Bye everyone.
Cool. Bye bye.